Newton's second law is something every physics student should know. Force is equal to mass times acceleration, right? But in AP Physics 1, that idea doesn't stop with straight line motion. Today we're learning about Newton's second law in rotational form, which explains why objects start rotating, speeding up their direction, or resist rotation. This topic shows up everywhere, in torque problems, rolling motion, and FRQs. So let's make it simple. So let's start off with some things that you have to know. Again, the Newton's second law. And this is in the linear form. So that is just F net is just equal to ma. So this is translational motion, right? So now let's continue with Newton's second law, right? So the rotational version is just going to be tau, which is this T symbol looking thing. Net is equal to the inertia times alpha, right? This is going to be angular acceleration, in case you don't know. This is moment of inertia, right? And this is just the net torque, as the subscript says, right? And this is the most important equation in rotational dynamics that you literally have to know, right? So now let's continue with what is torque again. I've mentioned this in previous videos, but let's just restate it again. Torque is the rotational equivalent of force. So essentially they do the same things, just in their respective angle versus linear measurements, right? So tau is just going to equal to r times f sine theta. And some things you need to know is that torque, depends on where the FA is. Again, think about like a door, right? You push it on the door. Like when you're pushing open a door, right? You push it on the handle versus you push it next to the hinge. It's going to be easier when you push it on the edge of the door. And also, same logic, forces through the axis, zero torque. Well, you can imagine that again, right? So this example was like the door hinge, right? So like you think about it like this. So, so greater. So imagine you push something right here. The torque is going to equal to 0 because there's no distance from like torque depends on the radius, right? So that's the radius is equal to distance, right? Distance from the axis of rotation. And if there's no distance times the axis of rotation, that r is going to equal to 0. So when you multiply 0 times f sine theta, that's going to equal to 0, right? So the torque is going to equal to 0. Makes sense. And again, because you see the radius, right? The bigger lever arm, yeah, that's going to mean a bigger rotational effect, right? Makes sense. So now let's talk a little bit about moment of inertia, right? So moment of inertia is a measurement. It basically measures the resistance to rotation, right? So that's going to be I is equal to the summation of mr squared, right? So basically, again, what does this mean, right? So the farther mass is from the axis, okay? The harder it is to rotate. Yeah, we know this, right? And again, let's go to our fifth point, which is angular acceleration. So angular acceleration, it tells you how fast angular velocity changes. And you can think of remember in translational motion, right? We remember that acceleration is just translational. We remember that acceleration is just delta v over delta t, right? So then it would make sense that in rotational is just alpha is equal to delta angular velocity over delta t again. Delta t is going to be the same. Those are just the analogs. Again, these are just analogs. Analogs you have to know. So, now, what we know is that from Newton's second law for rotation, we know that torque causes angular rotation. Or angular acceleration, I mean. So, what does that mean? Well, increasing force means increasing linear acceleration. And then if you Okay, and if you, that means also that, so essentially they're the same. Like if you increase the torque, which is tau, right? So that's going to be an increase of angular acceleration. So also just write that, like force, torque, yeah. And also we know that like bigger moment of inertia will mean that you have a smaller angular acceleration. Right, so again, this is why doors are easier to open at the edge, and that's why heavier or wider objects why are harder to spin, right? So now let's do some practice problems. Let's go over some examples to demonstrate these ideas. So let's start off with problem 1. A disk of mass m and radius r rotates about its center. A force F is applied tangentially at the edge. Find the angular acceleration. So we have this little diagram here, and you see the radius r, the mass m, the Fa applied here at a 90-degree angle. So we know that torque is equal to tau, which is equal to r times the force. And we know that the moment of inertia for a solid disk is just I is equal to 1/2 mr squared. So then using Newton's second law of rotation, we know that tau is just going to equal to I times the angular acceleration. So then we can replace the tau here with the RF we have up here, and then the I with the 1/2 mr squared, and then carry down the alpha. Then we divide both sides by 1/2 mr squared, so that we can just isolate alpha, and then we just have alpha is equal to 2f divided by mr. So what does this mean? It means that applying the force farther from the axis increases angular acceleration. And if you're wondering how the fraction division happened, well, just look, 1 divided by 1/2. When you have a number divided by a fraction, you just flip the second number, and then it's just the reciprocal, and then you just multiply the two, so that means it would cancel out. So then this is what would happen: 1/2 divided by 1/2, it would be 1/2 times 2 over 1, which is just equal to 1, as an example. And then we would have 1 divided by 1/2. This is equal to 1 times 2 over 1, which is equal to 2. Now let's do another problem. Let's go over to problem 2 first, actually. A rod is pivoted at its center, and a force F acts upward on the right end, and an equal force F acts downward on the left end. So let's actually draw this out. It's pivoted at its center, so that means here it goes up on the right, so F goes up, and then F goes down. So there's the direction of the torque. So both forces produce torque in the same rotational direction. So what does that mean? Well, it's being produced in this counterclockwise direction, and counterclockwise is the positive direction, actually. So we know that tau is equal to the radius times the force, and the radius just is just going to equal to the length divided by 2. So this is the radius, right? And then this is the entire length. So the length is just the radius is just equal to the length divided by 2. So then that means the net torque is just going to equal to 2 times the length divided by 2 times F. So that's just going to cancel out, and we just have the net torque is just equal to LF, because they kind of just cancel each other out. So we're back where we started. So now, what is the moment of inertia for a rod about the center? So that's just going to equal to the inertia is equal to 1/12 times ml squared. So according to Newton's second law of rotation, we know that tau is equal to the inertia times the angular acceleration, right? So that we know that tau is equal to LF, so we can substitute that in there. And we know that the inertia is 1 divided by 12 times ml squared times alpha. So dividing both sides by 1/2 ml squared, then we just cancel that out on the right side. Now you just have alpha is just equal to 12 times F divided by ml. Now let's go on to our last question. This one's kind of long, but I'll explain it. For problem 3, we have a solid cylinder rolls on an incline without slipping. Let's actually add a diagram to this. So we have an incline like this, right? And we have, it's a slope, and we have this cylinder that goes down, right? So if the cylinder, it goes down like, okay, this is kind of weird looking. This is the cylinder, right? And, okay, whoa. Cylinder goes down the ramp. This is actually not straight, I realize. this. So it goes down the ramp, right, at a velocity. So we want to find the angular acceleration of the cylinder. So we know that there's two different forms of acceleration, and we can define acceleration in terms of Newton's second law. But when we have these rolling motion problems, remember that the total energy of the system is actually split up into translational and rotational. So that means you have both translational and rotational energy. Therefore, you need to use Newton's second law to represent the total sum of the forces and the total sum of the torque in these two different subcategories. So we have, in the translational form, we have the net forces is equal to the mass times acceleration, and in the rotational form, we have that the net torque is equal to the inertia times the alpha, or the angular acceleration. And we know that the rolling condition for an object is equal to the acceleration. The acceleration is equal to alpha times the radius. So this relates the translational and the rotational worlds together. So then now we just want to isolate for just alpha, right? So then we divide both sides by the radius, and then we just have alpha is equal to the acceleration divided by r. And we also know that the moment of inertia of a cylinder, which you kind of have to just memorize and just know, is equal to I, which is equal to 1/2 mr squared. And now we also know, we can just take this equation here, write this to the side. Now we have tau is equal to the force times the radius. And actually wrote that twice. So tau, we can just and we know that the force is the same thing as the inertia here. So we can just substitute 1/2 mr squared there, and then we can substitute alpha for the radius, and then we have F is going to equal to 1/2 mr squared, and we have, this is actually kind of weird. That's F. Actually, this is something else, because torque, the colors are wrong, but the message is right. That's our second equation, and this was our first equation. Now we substitute the first equation into the second equation, right? So then when we do that, we have, here we had, like this equation here, this was 2. And then we substitute in, instead of alpha, we substitute in acceleration divided by radius. And then the radius, it canceled out right there. So then you have the F is equal to 1/2 ma. And now you want to substitute this F back into the translational equation, which is mg sine theta minus F, which is equal to ma. That's the net forces, which is equal to the mass times acceleration. So the F was equal to negative 1/2 times ma, which is equal to ma. And then ma can be written as 2/2 times ma. That's just 1. 2/2 is just 1. Then adding 1/2 ma and 1/2 ma, then easier represented as 3/2 ma. Then you multiply both sides by 2/3 to get the reciprocal and get that to cancel out. So now you just have, A is just equal to 2/3 sine theta. This is actually, this would just be A. And then now we want to convert, we have this in linear acceleration, but we want to convert this into angular acceleration. So we take the formula that we already have for angular acceleration, and we see that it has A, right? So then in order to just get the full expression for the angular acceleration, then you substitute in the linear acceleration into that form of the formula. So then that A is just equal to 2/3 sine theta. Substitute that in over there. You can factor out the 1/r actually to make it easier to multiply and just visualize. So then in your finalized form, you have that the angular acceleration is equal to 2g sine theta divided by 3r. Okay, and now for these types of rolling motion problems, you have to always remember that they require both forms of Newton's second law, which are rotational and translational energy. And also remember that not all gravitational energy goes into translational, and some of it goes into rotational. And that friction is also required for rolling, even though it does negative work. And because, friction is opposite the direction of motion always, so it's always going against the motion. When you push against the carpet, friction is acting in the opposite direction. It's pushing against your action of motion. And also, a larger radius means a smaller angular acceleration. So, think about, a larger radius of a circle, and you're pushing it, right? That it's going to have a smaller angular acceleration compared to a, when you have something spinning, and you have a huge circle, think of the Earth, versus a tiny little ball rotating. The little ball is going to be moving faster than the entire Earth, because, it's traveling linearly. It's traveling more. And then the Earth is traveling a lot slower, relative to its total circumference. And also, solid cylinders accelerate slower than point particles. And that's basically it. All right, thanks for watching. Let's actually touch on problem 3 a little bit more. So you might be wondering, how do we get the rolling condition? Well, you just differentiate v equals WR with respect to time. So then you just get A is equal to alpha times R, and then you divide both sides by R, and then in terms of alpha, you just get acceleration divided by R. Now, a little bit more about the diagram that we had over here. So in this situation, we know that the solid cylinder rolls down the incline without slipping. We know that friction always exists. So that because the cylinder is going down the hill, right? So it has to go against, there's a motion, there's like friction on the incline because it's not perfectly smooth, right? So like the friction is going to be going opposite. The velocity is going down rightward. The friction is going to be going up leftward at an angle, which the incline is at. So that means the friction force is going to be smaller than the mg sine theta, which is the force going down, because it has to be smaller. Because motion has to overcome friction always. And we know that because it's only going down the hill, it's not going through the hill because it's not like heavy or anything. That means we know that, we can write this. We know that Fn is equivalent to mg cosine theta, because the summation of the Fy is just equal to 0, because the net forces, they just cancel out in the vertical direction. That means only the horizontal direction is relevant, really, because it's not going through it, because you also have gravity here too, Ft, which is why you have to multiply it by that, because it's always it's equal to mg. And also we have mg sine theta, mg cosine theta there from trig. So we know that gravity acts down, and also pertaining to the, specifically here, like what we're focused on is the rotational motion, right? So because we're focused on the rotational motion, we had to focus on where the axis of rotation is. The axis of rotation is in the dead center of the cylinder. Because it's in the dead center of the cylinder, we see that gravity acts down the center of the cylinder from all points. So like just visualize that. You have a cylinder, and then gravity is always going to be cutting down right in the middle of it. So therefore, because it acts down the center, that means there's 0 radius from the center of the axis. That means that there's no torque, because you just multiply 0 times sine of theta. And also, you know that Fn also acts through the center, so there's also no torque from normal force as well. So that means only the frictional force causes torque. So because we know that, that's how you get this expression over here. So torque is equal to the friction times the radius, and friction times radius, so that's a torque. We know that torque, from the equation of torque, is equal to the inertia times the angular acceleration, right? And we know that moment of inertia is equal to 1/2 mr squared. So plugging that in, we can just solve for just the frictional force. We know the frictional force, which is actually, now I realize I should have made that a different color. These colors should actually be swapped. Let me actually make this a different color. This will all be pink. Okay, that was a little bit inconvenient. So this is all pink. And we're talking about the torque, right? This is all going to be pink to make that coincide with the, just like match with the other side, right? So we want it to, okay, stop this. We want it to all match, right? So we're looking at the torque. Again, I'm going to just highlight this so that it's like really like there. Only FF causes the torque. So because we know that only FF causes the torque, we can actually replace torque here with the frictional force. Let's actually write that there, FF, so you can see. Okay, that was weird. FF. So now we have what the frictional force is in terms of the inertia and the angular acceleration, right? So this is going to be our second equation, and then the equation we found over here is the first equation. So now you're going to sub the first equation, which was the angular acceleration, into the second equation, which was the frictional force equation. So now you have F is equal to, okay, let's add the F here, is equal to 1/2 mr times the angular acceleration, which is A over R, and then the R's cancel out. So then you have F of F is equal to 1/2 ma. Now you want to substitute, now that you have FF, you want to substitute this back into the translational equation. But you might be wondering now, like, how did we get this translational equation? Well, let's actually just like make this like a little neater. We can actually put this over here. So, well, use your knowledge from unit 2, and I'll explain this to you. So we know, again, from Newton's second law, we know from Newton's second law that the summation of forces is equal to the mass times acceleration, right? And we know that the force, we want to find the summation of the forces that are perpendicular to the incline. This means like perpendicular to the incline. So what it's referring to, and that's parallel to the incline, I mean. And this is perpendicular to the incline, right? So what we're focusing on is just like those horizontal things, right? That's just gonna be here. Again, these are just like in this direction, right? So that means we're just looking at the parallel stuff. So we know that mg sine theta is kind of like, is in this direction, going down. They're going in opposite directions. Because they're in opposite directions, right? You just subtract them. Yeah, awesome. Right? You literally just subtract them. So because you're subtracting them, yeah, and then you can substitute in like your f of f right here. You substitute in your f of f there. You have mg sine theta minus 1/2 mm mass times acceleration is equal to the total mass times acceleration. And you know, specifically, this can be rewritten as 2/2, because 2/2, you know, that's just equal to 1. Wow, awesome. And then you just add 1/2 ma to both sides. You want to combine like terms. Then you see that the mass cancels out there, so you cancel that out. And you want to just get, what do we want to get? We just want to get the acceleration for now. So we're trying to get the linear acceleration first. So that's our target, the linear acceleration. So then you multiply both sides by the reciprocal 2/3. Then you cancel out that 3/2 over there. Then you divide both sides by, and actually no, then you just have your answer. That's your acceleration is equal to 2/3 sine theta. But look, it's just acceleration. That's linear acceleration. We want angular acceleration. So your angular acceleration, you take the equation that we already had for angular acceleration, which we found up here, which was equation 1. Let's actually mark that. This is equation 1, right? And then you substitute in that a over here. So substituting that in, you can factor out the r, and that's just 1/r. So then you substitute a, that's 2/3 g sine theta. Then multiplying that all together, you have 2g sine theta divided by 3r. And that's going to equal to your angular acceleration. All right.